All right. Sorry about the delay. Welcome back, everybody. So I want to pick up where we left off. I don't know why this screen is dead. I apologize. But if you remember from last time, we were finishing up kind of discussion of scheduling. We talked about the SRTF scheduling, shortest remaining time first versus round robin. And what we saw here was an example where C would do a millisecond of computation and then 9 milliseconds of disk I/O. A and B would run for a very long time. And if we put a round-robin scheduler with 100 milliseconds time slice on this, what we see here is the disk utilization ends up only 9 out of every 201 time units, which is about 4.5%. We sort of said, well, if we got the round-robin up to 1 millisecond, we could get our disk utilization to 90%, but we're wasting a huge amount of time slicing. And then SRTF was much better because if we used shortest remaining time first, we would end up with getting the full 90% utilization without excessive time swaps. Were there any questions on this? So the biggest problem with SRTF, of course, is you got to predict the future. So that's kind of an issue. We talked a little bit about ways of predicting the future, including taking a history and building a Kalman filter or something like that. Now, the other thing that one can do is you can build something like a multi-level feedback scheduler where the whole point is to approximate SRTF. And if you remember, we have many queues here, highest priority at the top, lower priorities toward the bottom. And if an item is running in this top queue and it runs out of time, we put it into the next queue and so on. And as a result, long-running tasks tend to fall to the bottom, and short-running tasks tend to stay close to the top, and as a result, you get a sort of an approximation of shortest remaining time first, because the short ones are running toward the top. Were there any questions on this? Now, of course, the interesting thing about multi-level feedback scheduling is you can make it arbitrarily complicated, and people have. Okay? And we talked a little bit about the O1 scheduler, which technically had, 40 queues that were managed with some really complicated heuristics for moving things up and down. The other thing which I zoomed through really quickly was the Linux Completely Fair Scheduler last time. We kind of ran out of time, but this was the official scheduler as of about 2.6.23 version of Linux, and it was inspired by fair queuing, so every process given their fair share of resources rather than trying to figure out how to adjust priorities in some arbitrary way to get the behavior you want. And the way to think about CFFs is it's really modeling an ideal multitasking processor. And so the simplest thing is if I've got n processes running, an ideal multiprocessor would run all n of them at the same time, and so every process would get 1 over nth of the time. And they would furthermore be running fully in parallel with no multiplexing. And of course, this is not what you really have if you have only one processor. And so CFS's claim to fame here is this notion of virtual time, which is the time that each process has gotten on this ideal processor. Okay, and as long as every of the n processors all get the same amount of virtual time, then we've been fair to them. That's where the word fair comes in. And what you can imagine is you just take the actual execution time you've given one, and in this case maybe multiply it by n. So you're doing an n scaling factor, and that's the amount of time that it would have gotten on this ideal multiprocessor, because the multiprocessor is giving 1 over nth of the cycles to everybody. Okay, and so this is really literally the way this thing works if you have everybody running at the same nice level, and they have sort of some tricks with red-black trees and so on to essentially, when you're going to pull somebody off the queue, all you really do is pull the one that's had the least amount of virtual time so far. Okay? And this automatically tracks interactivity in some way, because if you're interactive and you go to sleep all the time, then you don't get virtual time. Everybody else does. And so the moment you wake up, oh, you're way behind. The scheduler says, I got to give you some time, and you get to go with high priority. And that's the essential way that this gets you that interactive factor. Okay, I realized I didn't talk about this a lot last time. I kind of zoomed through it. Were there any questions on this? Okay. And I think I asked before, but how many people have seen fair queuing before in another class, like 122 or something? Okay, so this should be fairly familiar. Okay. And then the final thing we talked about last time was real-time scheduling, where what's important is predictability, not necessarily efficiency. And we talked about hard and soft real-time, where hard real-time is really trying to meet the deadlines of all tasks. And we talked, in fact, about earliest deadline first. The idea here is literally that I know when something has to happen in order to meet my constraints. I have a good worst-case estimate of how long it's going to compute, and then the scheduler figures out of all the things that are sitting out there in the queue, how do I order them in a way that is likely to meet everybody's deadline? And earliest deadline first just picks the one whose deadline is earliest in time. And that's it. And that turns out to be very useful. And soft real-time is really that you try to meet the deadlines with high probability. And there is something we won't talk about in this class, I do in some other graduate classes and so on, constant bandwidth server, which is essentially using EDF to say I give a guaranteed fraction of the processor to your media decoder, and by the way, it has a lot of similarities to CFS in the grand scheme, which I just told you about. Okay. Were there any questions on that? Okay. Good. So a final word on scheduling. You know, we've been talking a lot about policy, and by the way, for scheduling policies, and by the way, we could talk about scheduling for weeks if we had the time. But you have to ask the question, when is it that scheduling actually matters? Okay, and the answer has to be when there aren't enough resources for everybody to go around. That's when scheduling matters, because otherwise it doesn't matter. Okay, all right? And you can simply ask the following question. You can go for a really, really sophisticated, and by the way, the one caveat to that first statement has to be in the real-time domain where your ordering might actually matter pretty essentially. But when should you simply buy a faster computer rather than trying to go for a more sophisticated scheduling algorithm? And this is a good question, right? We keep expanding the number of lanes on our highways here in the Bay Area to try to deal with throughput problems, okay? Because the queuing delays are bad, and no scheduling algorithm you can come up with on our highways are going to help. And so, you know, one approach is you buy it when it's going to pay for itself in improved response time. And so this is sort of an economic argument you could get into. And the thing that you should know about, and I'm going to say this several times this term, this curve is probably one of the most interesting systems curves you will ever see, and you're going to see it many times over your lifetime. And it's basically a curve that has utilization from 0 to 100% of any arbitrary resource and response time. Okay, and as you get closer to 100%, it's not linear. It goes up potentially to infinity. Okay? And that is a queuing response curve, and that tends to be lots of systems with randomness in them behave that way, that as you get closer and closer to using up 100% of your resource, your response time goes very non-linearly up in space. And we hopefully will have some time to actually give you a little bit of queuing intuitions later in the term, but this basically says never, ever, ever run something at 100%. Okay, because you're just in a bad position. You should run it kind of when this knee of this curve shows up, maybe around 70% or so. Okay? Never, for instance, run the bridge at 100% of its weight capacity. Okay? I guarantee that's a disaster waiting to happen, right? 100% is something that you should keep in mind as an engineer and never get close to, much less exceed. Okay. And basically, most scheduling algorithms that you could come up with work well in the linear region and at some point hit this nonlinear region and basically fall apart. And you should never be running in the nonlinear region of any of your scheduling algorithms. Okay, that's my final word on scheduling for now. Were there any questions? Yeah? Is this graph based on empirical data? Or? This graph comes from intuition with the universe. No, the question is, where's this graph come from? What's interesting about this graph is you can measure it empirically. You can do some queuing theoretic modeling. There's ways of doing some of that. I'll show you later in the term. I'll actually show you how to do a very simple queuing model. And they all have this behavior. where as you get close to that 100% point, you get this nonlinear response and things go up. And pretty much the only time you can get to 100% without running into this curve is if you have absolutely deterministic response time for everything in the system, and then you can kind of creep right up to 100%. But any randomness at all, and the long tails sort of collaborate against you, and you're in trouble. But so, answer to your question, you see it empirically, you see it analytically, you just plain see it. And so it's a good curve to keep in mind. Okay? Good question. I'll actually show you an analytical derivation that's simple later in the term for this. Okay. The analytical one, of course, it goes to infinity, which is pretty hard to wait for. So how do you measure it? Could be a good question. But all right. So now, where were we last time when we stopped? We were talking about starvation versus deadlock. And I wanted to start our sort of discussion by making sure we had these terms down. And it's interesting, I've had several people ask me questions over the course of the term, what's the difference between starvation and deadlock? And sometimes, by the way, live lock gets thrown in instead of starvation. But basically, starvation is any time a thread waits indefinitely. All right? Deadlock is a circular waiting condition that will never resolve. So a deadlock is a type of starvation. Okay? And here's a situation here where clearly I changed fonts and things are no longer centered, but other than that, you got thread A owns resource 1 and is waiting for resource 2. Thread B owns resource 2 and is waiting for resource 1, and you're basically never going to resolve. This is a deadlock. And deadlocks you can recognize mathematically typically by putting together the graph of resource dependencies and finding a cycle. Okay? So, is that clear to everybody? So deadlock is a type of starvation, not the other way around. And live lock is a type of starvation. Live lock is starvation. Okay. So starvations that are not deadlocks can eventually end. Deadlocks don't end unless you break the cycle somehow. So, break the cycle by taking the resource away from one thread and giving it to somebody else. That might be an example of getting rid of the cycle. It's probably going to violate the semantics of your system, because the whole reason that you're locking out, that thread A is owning resource 1 and locking out thread B is that thread A needs exclusive access to resource 1. So presumably if you took resource 1 away, thread A is going to have bad behavior. Okay? Now, conditions for deadlock are easy to come up with, but deadlock's hard sometimes to actually recognize because it's not always deterministic. So for instance, consider these two uses of the mutex, X and Y, and we're using, we're using semaphores initialized to 1 for this. But notice that thread A does an X.P and then a Y.P, and thread B does a Y.P followed by an X.P. And if you were to run thread A and thread B over and over and over again, and of course they're going to close out the end by releasing the locks, you could run this for a long time, and then all of a sudden, poof, you got a deadlock, because you end up with a situation at some point where A has lock X and is waiting for lock Y, and B has lock Y and is waiting for lock X, and it happens non-deterministically depending on your scheduler, okay? And it only happens once in a blue moon, all right? And how the heck do you debug this? Okay, so everybody see that this could be a problem. Do people see the cycle there? All right, and lots of such things happen. So deadlock doesn't always happen with this code. Have to have exactly the right timing, although I guess you could call that the wrong timing. And this happens all the time. You release a piece of software. You've been working on it for months. It's great. You love it. Getting lots of tweets about it, whatever. You put it out there, and the first thing that happens is it locks up on the first person that tries it. Right? Is that Murphy's Law going after you? No, it's just Murphy's Law. Yeah. That would be a great example of a Heisenbug, okay? Because it doesn't happen regularly enough to debug it. Okay, and this is a good example of something where you're going to have to either, and I'm going to talk about a bunch of possibilities today, either have ways of breaking deadlocks once they exist, preventing them from ever happening in the first place, or living with it and telling people to reboot their machines, which of course, Control-Alt-Delete is one of our favorite things to do with computers these days, right? So deadlocks occur with multiple resources. You can't get a deadlock without two resources. Okay, if you only have one resource, it's not a deadlock, it's something else. Okay, it's your program stuck in an infinite loop or something. So it basically means you can't decompose the problem simply in a way to deal with it either. And so it's really, lots of examples. Systems, 2 disk drives and 2 threads. Each thread needs 2 disk drives to function. Thread gets 1 disk, and thread B gets the other disk, and now you're stuck again. And there are lots of examples of this kind of thing. Okay? So here's a great example, the 1-lane bridge. And, of course, this never happens in California because we're all so polite. But here we have a situation where both sides try to go on the bridge at the same time. They're stuck. Right? What are you going to do? Well, each segment of the road is a resource. Car has to own the segment under them, and they have to acquire the segment they're moving into to work. And for the bridge, you have to acquire both halves of the bridge. And here we have a situation where this guy has acquired the left half and doesn't have the right half, and this guy has acquired the right half and doesn't have the left half, and we've got a cyclic problem. Okay? And if the deadlock occurs, you can resolve it in various ways. So one of the cars could back up. Okay? Probably the one that flinches first is the way that works in California, right? No. Everybody politely backs up, so they both back up, then they both go forward and get deadlocked again. I don't know. So it's possible that several cars have to back up to resolve this. Starvation's possible here because east-going traffic, if it's going really fast, it may be that west-going traffic never makes it through. Okay? So that's another example of starvation. All right. Questions? So now here's an example of a train that is very similar to something called wormhole-rooted networks. And basically what you see here is the trains, which have multiple cars attached to an engine, are trying to make a turn. So this train is going east and trying to go south. This one's going south, trying to go west. This one's going west, trying to go north. This one's going north, trying to go east. We're stuck. Everybody see that? Can everybody see the cycle in there? That one's not too difficult. So there's a circular dependency here. Each train wants to turn right and is blocked by the other trains. This is very similar to the multiprocessor mesh networks, which you may have encountered in other classes. So you imagine the grid extends in all 4 directions, and what we do is we force an ordering of the channels. Yes, there was a train that just did that. Did everybody catch it? So we force ordering of channels to make sure that this doesn't happen. So the protocol could be always go east-west first and then north-south. So basically, always go east-west first and then north-south means that there's never going to be a cycle because this train is violating the rule. They're trying to go north first and then east. What you would require them to do instead is do all of their eastern traveling this way and then go north. Okay, and so by this fixed ordering of channels, always go east-west first and then north-south, you avoid a cycle. And by the way, this is called dimension-ordered routing, and networks do this. Okay? Dimension-ordered routing. Questions? So there, I've removed the potential for deadlock kind of by law. Thou shalt not do anything, go north and then east or south and then west. Okay. So here's the dining lawyer's problem. 5 chopsticks, 5 lawyers. Really cheap restaurant because there's only 5 chopsticks, right? So the free-for-all, the lawyer will grab any one that they can get, but they need 2 to eat. Okay, and let's ignore we'll have some really good alcohol to dump them in or something, whatever. So what if they all grab at the same time? Everybody gets 1 chopstick. We got deadlock, right? Because they're not going to give up their chopstick. Okay? So what are you going to do? Well, how do you fix the deadlock? Well, you make one of them actually give up the chopstick, and eventually everybody gets a chance to eat, right? Because if one of them gives up a chopstick, now somebody's got two they could eat, then they put their two chopsticks back, and so on, and suddenly everybody's got a chance to have two chopsticks at some point. Okay? How do you prevent deadlock here? Well, you can come up with a rule. Here's a rule. Never let a lawyer take the last chopstick if no hungry lawyer has two chopsticks. Think that again. Never let a lawyer take the last chopstick if some other lawyer doesn't have two. Why does that help? Yeah. That's right. So here we're literally preventing starvation, yes. Why will somebody make progress for sure? There's two clauses here, right? So if we don't let them take the last chopstick, then we know that at least somebody probably has one chopstick. We can combine them together and eat. Or if we let them take it, then some other lawyer's got two chopsticks, they eat and put them back. Okay, and in both cases, we know that forward progress will be served. Okay. Now, by the way, this particular rule here is a special dining lawyer's case of a way to prevent deadlock. I'm going to show you a little later. Okay, questions? Now, 4 requirements for deadlock to even happen at all are 1, mutual exclusion, which basically says only one thread can use some resource at a time. So we have a resource that can be exclusively owned by a thread. And notice, incidentally, that a resource could be a critical section, and so that's why we had our locking example earlier, or the bridge example. Hold and wait says that a thread holding at least one resource has to be waiting to acquire an additional resource. No preemption says that I'm not allowed to take away a resource from somebody, okay? And this is typically the case where a resource is exclusively owned for some period of time and then released. That has to be a property, because if we can arbitrarily take resources away at any time, then we're not going to deadlock. And then finally, we have to have a circular wait situation. So there exists some set of threads, each of which waiting for a resource held by the next thread, and you can go in the loop. Okay, and that will give you a deadlock. And if you have to have all 4 of these to actually have a deadlock. Questions? That make sense to everybody? All I've done here is sort of formalize the cycle I showed you earlier. Now, we can actually do this even further. We can come up with a resource allocation graph, and I'm just going to show you this briefly here, but a set of threads, T1, T2, T3, Tn are going to be circles with a thread number in them. We have a set of resources, types, R1, R2, Rn, and the number of dots in a given resource type is the number of instances. So for instance, there might be 3 printers, 1 disk. Okay, so printers are R2, disks are R1. And so in this instance, I'm going to assume that every one of these instances of an R2 are interchangeable with each other. Okay, and if you want to, not worry about that, I could go to the fact that there's a bunch of resources that only have 1 copy of themselves, and we have a bunch of squares with a single dot in them. But it gets more interesting if there are more options. Okay? Now, each thread utilizes a resource by requesting it, using it, releasing it. So we're assuming this is very similar to our lock, critical section, unlock. Very similar. In fact, it's identical. And the resource allocation graph is like this. We can say that the graph is partitioned into 2 types of nodes, circles and squares. And a request edge is basically, here this says that thread 1 is requesting resource J, thread I is resource J, and an assignment edge says that resource J is owned by thread I. Okay, resource J owned by thread I. Or the other way to look at this is called a waits for graph. So thread 1 is waiting, or thread I, this should be an I, is waiting for RJ, and RJ is waiting for TI to release it. Okay? Thread 1 is waiting for RJ to be released. That's what this arrow means. Okay? And so now we can just do this. Here's a simple resource allocation graph, right? So what do we see here? What we see is Resource 3 has two identical instances, one of which is owned by T1, one of which is owned by T2. T1 is waiting for resource 1, which is currently owned by T2. T2 is waiting for R2, which is currently owned by T3. And by the way, T3's also got a copy of R4. Okay, I can see all that from that graph. Is everybody with me on there? Now, of course, the reason I bring graph theory into this whole thing in the first place is that then here's a deadlock, right? Why is this a deadlock? Well, because there's a cycle in the graph, right? Here's T1, it's waiting for R1, R1's owned by T2, T2 is waiting for R2, R2 is owned by T3, T3 is waiting for some R3, but this R3 is, both R3s are tied up by T1 and T2. And so if you were to work your way through here, there is a cycle that's non-resolvable no matter how you slice it. Okay, now stare at that a second, and are there any questions? Everybody see that there's basically a deadlock in here? There's more than one cycle in here, but there's at least one, and it's not resolving. Yeah?
So is it like a if with two F's? So like if there's deadlock, then there's a cycle that also ends?
Yes, all deadlocks have cycles. But not all cycles are deadlocks. So it's not an if and only if. And here's a great example. So here's a cycle, but no deadlock. Okay, so if you look here, T1's waiting for some R1. One of the R1s is owned by T3. T3 is waiting for some R2. One of the R2s is owned by T1. Here's a cycle. Why is this not a deadlock? Yeah. There's two resources, and so all we really have to do is wait for T2 to finish. It'll free up some R1, which T1 can now get, and we're going to make forward progress. Does everybody see that? Good. Now, how could we know that there's no deadlock there? Oh, Professor Kuby says that there's no deadlock. So, two problems with that theory. One, if you got this on a test, I would not probably tell you whether it was a deadlock or not. And two, I know it would be nice, but I won't always be there for you to recognize your deadlock. So how could we go about figuring out whether there's a deadlock there or not? Do you see what I did? I simulated, right? I said, oh, yeah, T2 can run. Let it run all the way to completion. It'll free up an R1. And then I say, oh, T1, get an R1. It can now run to completion. Now it'll free up R2. Now T3 can get R2. It'll run to completion. I can simulate my way through the pot of resources and eventually find out that all the threads are done. Okay? And so that's the way you would do this. Okay? It's basically doing a simulation of what needs to happen. Okay, any questions on that? Okay, so what are some methods for handling deadlocks? So one is we just let it deadlock and recover. Okay, so this has got to have both a deadlock detection algorithm and some technique for forcibly preempting resources. So once a deadlock occurs, the whole reason it's a deadlock is it'll never resolve, and therefore I have to resolve it forcefully. Okay, not everybody's going to be happy. Somebody give me an example of how to forcibly preempt resources that you may have heard of before. What is a method of recovering from deadlock that you may have heard before? Anybody think of any of these? Reboot, yes. What's a less drastic one? Yes? Yeah, you do a database rollback, right? You roll back to a previous state, start over again. Good. You could ensure that the system never enters deadlock. That was that sort of cyclic example I showed you with the trains where we make sure that certain arcs never happen and therefore it's impossible to ever have a deadlock. Okay? And then the other is we could ignore the problem and pretend that deadlocks never occur. And this is really, unfortunately, what a lot of operating systems do. And this is really the category of reboot, kind of. It's like, well, it's locked up. I don't know what's actually wrong. Control-Alt-Delete. Okay? All right. Now, midterm 1. We actually have a room. It's coming up a week from Wednesday. Dun, 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 dun. So it's going to be March 11th. It's from 7 to 10. We actually have 2 rooms, which we haven't figured out how we're assigning people to rooms yet. We'll figure that out. I'm sure you've all dealt with this before, Pimentel and Valley LSB. All topics up to and including next Monday are technically fair game. And closed book, 1 page of handwritten notes, both sides. Okay, questions? Yes? Is it going to be more theoretical or more based on the project? Yes. Assume some of both. Yes. No class that day. Oh, I forgot to put that in there. Okay, no class. No class. This is called on the fly. And I'm going to put that day in there instead of saying there's no class. Kubi has no class. Okay, no class a day. And I'll actually have probably some extra office hours during normal class time. Yes, question? Oh.
How much is this exam worth?
This exam is worth 1/3 of the 40% that the exams are worth. So there's a first half of the term, second half of the term, all of the term, final. So, and this is, by the way, I didn't put this in there either, but it's essentially a 2-hour exam over 3 hours, so you have time to think. Now, one thing I may require of you is to bring a calculator, and I'll tell you that on Wednesday or whatever. Yeah, go ahead. Yes. We haven't scheduled it yet, but there will. Well, would people prefer to have this on the weekend or during weekdays? How many people for weekend? Okay, how many people for weekday? A couple of you. All right, I'll see what I can do. Probably weekend is more likely, but okay. The other thing is, you're probably all aware that we've moved Hardware 3 forward a week. Part of the reason for that is Homework 3 is basically using material that you haven't heard yet, so we figured it was probably better for you to push it forward. So, okay. I don't actually have any other administrivia. Do we have any other questions? No? Okay. So let's talk about deadlock detection here for a moment. So only one of each type of resource, actually you can look for loops. So I said earlier loops are not enough, but yes, if you only have one of each type of resource, so only squares with a single dot in it, loops are enough. But if you have something else, you need a more general deadlock detection algorithm, and I already showed you what this is, or told you. So basically what we do is we take all of our resources, R1, R2, whatever, and put them in a vector, one element per resource type, and that is sort of the number of free resources of each type. And then a given thread can request resources, and it will also be a vector of as many resources as there are. And we have the current resources that a thread has. So thread X is requesting resources and has got some already allocated, and we have some free. Okay, so all 3 of these vectors have as many elements as we have resources, namely 2 in this example. Okay, and then all we do is simulate. We start with the vector is all free resources, and then we put all nodes, that means all of the threads, in unfinished list, and then we go through, and we say basically for every node in the unfinished list, if the things I'm requesting, so those are the forward arrows from a thread, to a resource, are available, then go ahead and assume you can simulate that node to completion. Remove it from the unfinished list, put all of its resources back in the available pot, and keep looping. And you just keep going until you hit a situation where nobody's making any forward progress, or until there's nothing left in the list. Yeah, go ahead.
When would this deadlock detection algorithm run?
Well, that's a good question. So when would the deadlock detection algorithm run? You'd have to run it based on when you allow resources to be allocated. So the way I've got it described right here now, this is an instantaneous point in time saying, are we deadlocked or not? Okay, and you could think of this as sometimes it's called, am I in a safe state where everybody could finish at this instant in time? Okay, or you could say as long as the only thing I ever request is the last thing I'm requesting, then this really says that this will never deadlock through the rest of the time. I mean, there's lots of ways you can look at this. Okay? And we're actually going to take, that's a great question though, we're going to take this deadlock detection algorithm and turn it into a deadlock prevention algorithm in just a moment, doing essentially what I just said, but in reverse. And I'll show you that in a sec. Questions on this? So the thing that may be confusing about my notation is anything with brackets here, these are vectors with the number of elements equal the number of distinct resource types. Okay, and so this is all vector addition and vector comparisons and so on. Yeah, question?
How do we know when this won't work, as in when there is a deadlock?
The way you know there's a deadlock is you keep going until, so notice what we've done here is we say done is true, and every time we pull somebody out, we set done to false, and as soon as you don't make any progress, you fall through, and then you look, and if the list is empty, you win, and if it isn't, you lose with a deadlock. Does that answer the question? Yeah. So it's kind of the done variable here is, am I making progress? Am I making progress? And as soon as I'm no longer making progress, then I look and I see is the list empty or not. And if it's empty, then everybody's done and it's not deadlocked. It's a good question, though. Okay. So what do you do when you detect deadlock? So we talked about this a moment ago. So you can terminate the thread, force it to give up the resources. So the bridge, Godzilla picks up the car and hurls it off the river. You solve the deadlock. Shoot a dining lawyer. I guess then you reach over and grab his one chopstick or something. I don't know. Not always possible because killing a thread holding a mutex can leave the world inconsistent. Okay, so you could preempt the resource without killing off the thread, just take it away, but that's often doesn't fit the semantics. And then we talked about rolling back from a database standpoint. So these are all options. All right. So many operating systems use lots of options of deadlock, what to do with deadlock, and including, I suppose, it could put up a little pirate face. Oh, you're in deadlock. Reboot, or something. I don't know. So what are techniques for preventing deadlock? So infinite resources, actually it turns out if you have an infinite set of resources, there's no way to ever deadlock. Now, I know it seems silly for me to say this, but if you think about it, that means no thread is ever waiting for a resource as a way to prevent you from getting deadlocked, because the only types of deadlock we've described are thread, resource, cycles. And if you can't have any threads waiting for resources, you can't possibly have deadlocks. Okay, and the slightly more practical notion of this is if you have the ability to increase your resource pot sort of on the spur of the moment, you can often take a deadlock scenario, throw a couple of extra resources at it, and unwind the deadlock, and people will move forward. And that's essentially like having infinite resources. Okay, but it's not always an option that you can go after. Another is you never share resources, and of course I've been hopefully indicating to you throughout the term that while not sharing resources makes everything nicer and easier to think about, nothing does that, okay? And so then the other thing is never allow waiting. So if you think about it, if I am never allowed to wait to get a resource, then I can't get a deadlock either because there's no thread to resource wait arc. And there's lots of good examples of this, okay? How does the telephone company avoid deadlock? Believe it or not, anybody in this age of cell phones, anybody ever gotten a busy signal? A couple of you. It happens to me once in every long time, and it's like, wow, that's cool. Usually I'm annoyed immediately afterwards, but what that means is that there isn't a path, and what they've done is they've rejected your request. Rather than making you wait, they've rejected the request all the way back. And so there is no way to get a deadlock cycle in a telephone network. Okay? And this is also a technique used in some of the Ethernet networks and some multiprocessor networks. It tends to be inefficient if you use it on a large scale because you keep retrying. Try again. So rather than deadlocking, what you've done is you've pushed it back on the originator to keep requesting. Okay, and so it's almost like you've turned a deadlock potential into a live lock that's not a deadlock, but it's still wasting resources requesting over and over again. Okay? Now, what am I doing here by preventing deadlock? I'm taking the 4 conditions for deadlock, and I'm removing one of them. Don't wait. don't get cycles, whatever. And by removing one of those 4 conditions, you don't end up with a deadlock. Okay, and so that's kind of when you say, how do I prevent deadlock? It's like, how do I prevent those 4 conditions from happening? Now, another thing is, I could make every thread request all the resources they could possibly need at the beginning, and then I just plain put them on some queue, and until all their resources are ready, I don't let them move forward. There's no deadlock because they're waiting to be scheduled. They're not in a loop with anybody else. Okay, so for instance, if I need 2 chopsticks, I request them both at the same time, and until I get both, I don't take one of them, I don't even take one of them. And it turns out that you won't end up with the dining lawyer's deadlock in that case because there is no way to actually be deadlocked on resources. Now, interestingly, you could make sure that you never leave home until nobody's using an intersection between here and the Bay Bridge as a way to make sure you're never waiting for the Bay Bridge, but you can sort of see why that point might be unfortunate. The other is to force all the threads to request in a particular order, and this is actually what we kind of did with the train example, but this is a little more formalized. So if you've got resource X, Y, and Z, what you say is you're never allowed to request in anything but increasing order. You first ask for your X, then your Y, then your Z. Can somebody give me a proof why that will never deadlock? If we make threads ask for X first, then Y, then Z, why is it not possible to deadlock? Good. So the first answer is you can never deadlock without a cycle. You said deadlock requires a cycle, Professor Kubi, therefore we can't do it. But why is there no cycle? Yeah, the only way to get a cycle is if some thread is waiting for a resource that's owned by some other thread which is waiting for a resource. If you look through that cycle, what you'll find is any cycle you can come up with would require a thread to own a later resource but be requesting an earlier one. You should sketch it out on a piece of paper. You'll see that that's true. So there is a way to actually formally show that if you request the resources in order, there's absolutely no way to ever deadlock. And this is a good rule of thumb to remember. If worse comes to worse and you're worried about deadlock, you can always pull this trick because there's no way to get a cycle out of it. So in the previous slide, I was preventing deadlock by removing waiting. In this slide, I'm preventing deadlock, at least down here, by removing the cycle aspect. Okay? Good. So this is what we just said. Here's the train example, circular dependency. Each train wants to turn right. But what we've done here is we basically force the ordering of the channels, as I mentioned, and we're essentially saying you always have to request your X channels first and then your Y channels. So you request an X channel and then a Y channel, and if you don't do that in that order, then you could cause a deadlock. And by the way, does anybody pick up on the somewhat subtle requirement in what I just said here? I'm assuming that every track I'm showing you here is bidirectional, right? So there's actually 2 channels to request, an X going left and an X going right. Okay, think through that. If the channels only went in one direction, then we would require somebody to possibly have to go all the way around the world to make certain destinations, and now suddenly I've got a cycle again. Oops. Okay, so you have to think about what type of network you've got. This particular type of network allows trains in both directions without blocking. Okay, good. So here's the banker's algorithm. This is the last thing I wanted to say about preventing deadlock. And basically, the right idea here, which is not going to be quite what we do, is to state the maximum resource needs in advance and then allow a thread to proceed only if the available resources minus the number I request is greater than the max remaining that may be needed by anybody. Okay, now that seems messy, but to break this down, what we're saying here is that if I get what I asked for, and I look at what's left, what this says is there's enough left for everybody else to still finish. And therefore, by getting my requested resources, I'm not locking the system up. Okay? Now, what we really want to say for the banker's algorithm, it's a little less conservative, and it says basically allocate resources dynamically and evaluate each request for resources and grant it as long as some ordering of threads is still deadlock-free afterwards. So what I'm going to do is very simple. I'm basically going to pretend, this is a thought experiment, I pretend that I grant those resources, and then I run my deadlock detection algorithm, and as long as the graph is not deadlocked, then it's okay to give those resources. If the lock, and by the way, I show you here that, you're basically substituting where it says this in the deadlock detection algorithm, put this sucker, but no worries. Essentially, the intuition here is very simple. I try it. Okay, suppose I give Joe his 2 resources. Now let's look at the rest of the graph. Does the graph finish? Oh, it's not deadlocked, therefore it's okay to give Joe his resources. And that's essentially all there is to the banker's algorithm. Okay, and it keeps the system essentially in what you can call a safe state, which is there always exists for every transition a way through a set of threads that thread 1 finishes, then 2, then 3, then 4, that eventually finishes all threads, and therefore we're not deadlocked. And that's what the banker's algorithm is. And why is it a banker's algorithm? Well, because it's accounting. Okay, it's all about accounting. And think about this for a moment. Dining lawyer's problem, right? What did I say? Never take the last chopstick if no lawyer has 2 chopsticks. If you think that through, the thought experiment is, suppose we give Kubi a chopstick. Okay? Is it in a safe state? Well, it's in a safe state if some lawyer has 2 chopsticks and therefore they can finish and put them back and then at least everybody can finish sequentially. Or if I am not taking the last one, then we know for a fact that there's one left there and it could be me taking it. I'll finish, put things back, okay? And so basically that rule about the dining lawyer's problem is just the banker's algorithm applied to that problem. Okay. Questions? How would you actually do this? Suppose you're doing this in Pintos. What would you do? There you go. Every time you request a resource, you run the banker's algorithm, and you either allow the resource to be grabbed or you put somebody to sleep on a queue. That was the next part you were going to say, right? You put them to sleep if they can't get the resource, and then when resources become available, you wake them up again. And as a result, the only thing they're not waiting on somebody else, they're asleep, and so you can avoid the deadlock that way. Yeah. Good. Okay. And so here's an example, and we just did this. Safe won't cause deadlock when either it's not the last chopstick or is the last chopstick, but somebody will have 2. There is the dining lawyer's solution using the banker's algorithm. And, of course, if we got a K-handed lawyer, and I'll avoid lawyer jokes, but you get the picture. Don't allow if it's the last one and no one would have K, or it's the second to last and no one would have K-1, or so on. Okay? Good. Any questions on this? Yeah. Doesn't this introduce a lot of overhead? Well, yes. But it's a question of sort of, do you believe deadlock is more painful than rebooting your system when it locks up?
But assuming if, let's say that everyone just follows the style guide and we all declare our resources in perfect order, right? Then we wouldn't need to do it.
The style guide, yes. So, I'm giving you a set of possible ways of avoiding deadlock. Banker's algorithm is by far the most resource intensive, no pun intended. I mean, you're doing a lot of computing, right? But what it does is it lets you run the closest to the edge in terms of getting close to deadlock without actually deadlocking. The circular dependency avoidance that I showed you earlier will always work. The problem with it, and this is why most networks these days, back when I was designing multiprocessor networks, they did the circular dependency, but they haven't done that in a long while. And why is dimension ordering maybe not terribly desirable to do as a general policy? Yeah. It's not so tough to, let's suppose you can agree on an order. I mean, X and Y. In fact, slight relaxings, well, let's not, I won't say that. Yeah, X and Y is not hard to agree on. Yeah.
Would you end up with more traffic? Like, would it cause problems with aggregation traffic across the network?
Yeah. So the real problem here is that it creates bottlenecks in the network because you're ferreting traffic through well-defined corridors to meet the constraints. Whereas what you'd really like to do is a free-for-all, go any way you want, and deadlock will only sometimes happen. Right? And so what you do in a typical network is you actually have multiple special tracks. You do a free-for-all in the main tracks, and then whenever you get to a position where you might be in deadlock, then you do a dimension order just for those cases that might be deadlocked. And what you get is the free-for-all gives you high performance, and you get out of the potential deadlocks, which are rare, with the separate channels. And that's typically what's done in a network today. Okay, so the real problem with prescriptions like dimension ordering is they often constrain usage for something that might or might not happen, will happen rarely. And so that's why you might not want to do it that way. All right, it's time for a break. Let's stand up, contemplate infinity, talk to your neighbor. All right. Let's change gears. So I want to now talk about resources. And the reason we, in general, and we've talked about resources kind of in the abstract with deadlock detection algorithms, but in reality, you have lots of processes or threads that are all sharing the same hardware. They're certainly sharing the same CPU, and we've been just talking about scheduling, but they're also sharing the same memory, they're sharing the same disk devices, and so on. And we need to figure out good ways of virtualizing these resources so that these different processes and threads can use them. Now, scheduling, as I just mentioned, is a way to look at scheduling is it's a way to virtualize the CPU so that it looks like each process or thread gets its own CPU. How do we do that with memory? And that's kind of today's topic. And you might, first of all, ask why even worry about memory sharing in the first place. And, of course, the complete working state of a process or the kernel or program or whatever you come up with is defined by the data in memory and registers. So memory is pretty important. Okay? And consequently, we can't just let different threads use the same memory unless we want them to. And of course, in physics, there is this sort of idea that two different pieces of data can't occupy the same location in memory. Okay, I don't know how profound that is, but let's make sure that any solution we come up with avoids that particular little snafu. By the way, if I end up, sometimes I do a final lecture that's just for fun, and we could talk about quantum computing where it's not clear that that's the case. But anyway, we'll go on. Probably don't want different threads to even have access to each other's memory, and that's a protection issue. So we've already talked about that, right, a little bit. And so our next objective, back to our little spiral, is we had our introduction, we've come out of concurrency, and we're now kind of going to really push on address spaces in memory quite a bit. And we're going to dive deeper into these concepts. And once we figure this out a little bit more, we have all sorts of things we get out of how we multiplex memory. We get protection, multi-programming, isolation, I/O efficiency, sharing, all sorts of stuff. Concepts that we get when we start talking about address spaces, address translation, and so on. And so we're basically about to pick a key mechanism that takes us a long way toward other things in the course. And today we're going to talk about linking and segmentation and page virtual addresses to some extent. So, if you remember, this was a diagram from the beginning of the class, and the distinction here was that threads encapsulate the concurrency, and so it's the active component of a process. And more importantly, however, the address spaces encapsulate the protection aspect. And if you notice here, the address space is this box around the whole thing, and in a single thread process, the address space is shared by only one thread, and in the multi-thread, it's shared by multiple threads. But the key thing is that we're somehow going to draw a box around each process and make sure that it doesn't interfere with other processes. And it's now time to really push on how that works in more detail. Okay? Now, some important aspects of memory multiplexing in this way are three of them I'm going to mention here. One is controlled overlap. So the separate state of the threads shouldn't collide in physical memory. Okay, and conversely, we'd like the ability to overlap for communication when desired. So we really want to control when threads share memory and when they don't. And that's going to be partially the process of being careful when we place our stacks and so on, so the threads are not running over each other. And then later, it's going to be how to control the mappings of memory so that threads in two different processes can talk to each other in a controlled way. So the second thing is translation, which is the ability to translate accesses from one address space to a different one. Okay, and the first address space is we're going to call the virtual address space. This is the one the threads think they're in. And the physical address space is the one that's for real and actually being used. Okay, so virtual, real. Okay, and we're going to try to keep those separate. I know that it's hard to keep virtual and life and real life separate, but let's try to separate them at least for this lecture. So when translation exists, the processor is basically going to use its virtual addresses as if they were real addresses, but then there's something in there, physical hardware or software, that's going to translate it to the physical hardware underneath and help us avoid overlap. Okay? And the third thing is protection, and this is preventing access to private memory from one process to another unless that's actually what we wanted to happen. Okay? Are there anybody that have questions about these three things? Controlled overlap, translation, protection. Okay. Now, if you remember from the very beginning, one of the key things we talked about was you can talk about software, you can talk about the operating system, but until you actually load the program into memory, it doesn't actually exist, right? It's a program as opposed to a process. And so here it's sitting in storage. We actually have to pull it into memory, and in many cases we have to do something with it, link it in some way. In order to make it something that the processor can actually munch on, we have to allocate stack, we have to do all sorts of stuff. And then, once we've done that, then we have a process. But until we do that, we only have some bytes on disk. Okay. Now, by the way, way back when, I actually was in a case, an expert witness case, where the key thing was whether the bits, ones and zeros on a disk, of music were fundamentally different from the ones and zeros on a disk that were a program. And it turned out zillions of dollars hinged on whether those ones and zeros were different or the same. So how many people think that the ones and zeros that are on a CD are fundamentally different from the ones and zeros of an executing program? How many people think they're the same? Okay, good. You've just restored my faith in Berkeley students, but you would have lost this case. Anyway. So, let's first talk about, that's a whole another interesting story, but let's start, first of all, with talking about what happens during that loading process. And what I want to do is I'm going to give you some assembly language for a second. And if you look here, we've got some labels on the left with colons and then some assembly language instructions. And it turns out this is just MIPS assembly, but, it doesn't matter. It could be Intel assembly. And this is really not executable because, first of all, this is a bunch of symbols, okay? And the processor doesn't know what to do with these symbols. So what's the first thing we have to do with this? We have to assemble it, right? So it gets assembled into something that looks like this, where here's an address, and this is hex 0x, by the way. These are addresses, and this is the data, 32 bits of data in the address. And what does this really mean? Well, what's interesting here is this data word basically is the decimal number 32 is actually a 0020 in hex, right? You guys are all completely comfortable with hex. Yes? If not, be a good time to get going. So, and that's in some address. And so notice that this data storage area with a number in it got mapped to an actual physical address that had the number 32 in it. By the way, 20 hex is 32. Who did that? Well, that was the assembler and the linker. And notice even more interestingly here is a case where we say load word from something that is that data address. And notice that load word had some binary stuff, which is the actual load instruction, and an offset 00C0, which actually points it there. Okay, this is 0300 hex. It turns out 00C0 shifted by a couple of bits is really 0300. And so part of assembling and then loading into memory is actually deciding where this is in memory and matching everything up and resolving all the addresses and everything, okay? And so the two red pieces actually map that load word instruction with the address of that data 1 and make it work. Now, I'm not expecting you guys to be able to do this assembly. That's what assemblers are for. But notice this process of going from the symbolic representation into a binary representation and then loading it into memory and specializing it depending on where we put it in memory. Okay? So I hope you all appreciate that, but that's actually what has to happen. So the fact that I'm putting this starting at 0300 actually causes some changes to happen in the binary when I load it in to make it work at that address. Okay? Questions? Now, fortunately, you don't have to do this by hand. I used to do it years ago because I could, but it's not fun. Okay? But, and here's another interesting thing. Suppose we want to load this thing at a different physical address. What happens? Yeah, anybody? Go ahead. Yeah, well, not only do you have to shift it, it looks different. Look, here, it's actually different. So if you were to look at these numbers, the binary of the instructions is different because of the offsets encoded in them because I put it somewhere else in memory. So the couple of high-level bits to get out of these slides is there's actually some really interesting stuff going on between the source code that you write, the assembly that produces a binary format that's relocatable, and then the final form that's loaded into memory based on where it is. All of that has to happen to generate things that the processor can actually execute. Okay? And the other interesting thing to take from this is, let's suppose that both this thing I called AppX and this thing down here are the same program. But I've loaded it into two different places in memory. The binary is different. Now I've got a few startled looks. Okay? Why is the binary different? Well, the simple answer is it's in a different place in memory. There's a little more profound answer there. What's the more profound answer as to why it's different? Shouldn't it be the same? How many people thought it should be the same when I loaded it to a different part of memory? Good. No, none of the rest of you guys? Why? You expected it to be the same. Why?
Because it seems like a lot of complexity to put on like this the software to know where it is in physical memory.
Yeah.
Keep track of like where the things are mapping to. Like you already put it in the zeros and ones. You should be able to like stay that way at work.
Now, right, so that's good. The other thing is, when you think about it, normally what you do is you compile the program, you get an A dot out, you link it, you get a binary, and you run that binary. Okay? And you're sort of thinking the binary is the same. What's missing in all of this is there is no translation of addresses, and so the processor is working in real addresses, not virtual addresses. And because we have no virtual address space in this slide, we have to relocate the program every time we load it to a different place. So you can see why maybe translation would be a really nice thing to have, because then our binaries could be independent of where they are in memory. Okay, now let me look at this in a different way. So basically, when you prepare a program for running, you compile things, then they get translated during link and load time and at execution time. All of these phases lead to the final binary that's executing. And if you look at this diagram, you start with your program that you write in C. It gets compiled or assembled, compiled in that case. It turns into an object module. That's a .o file. That gets linked with a bunch of other object modules to produce a load module, which then is loaded. And oftentimes, when it's loaded, it's put into memory. There's actually this last phase where it's linked up with dynamic libraries. So when you use the C library or a lot of those things, oftentimes they're dynamically loaded in memory already, and when you start the program, the first thing that happens is it's put into memory and it's actually linked to the version of the C library that's already loaded into memory. Okay? And so addresses that I showed you earlier can be bound to the final values anywhere in this path. So I was showing you them getting bound by the loader. Maybe they get bound mostly in this link phase, but certainly there are some addresses that don't get bound until you start calling the dynamic libraries. And so there's a lot of interesting phases here. Okay, and how many people have heard of dynamic libraries before? Okay, a few of you. So a dynamic library is a special library that's been compiled in a way that can be shared by many programs at the same time, and it's already loaded into memory at the time you start your program. And what really happens is the program starts executing as if it was linked with the library, but as soon as it hits a stub, the stub says, oh, I want printf. Oh, there is no printf. It actually goes off and finds printf that's already in memory, links it at that point, and starts running. So the stubs are actually resolved on the fly. Okay. So hopefully we all appreciate some of the interesting things that happen now when your program executes. Now, of course, you use GCC and you do -o and something and you run it and it works. Okay, but there's actually some interesting process that goes on here. And when you're done, of course, you actually have code that the processor can execute. Otherwise, there wouldn't be much point to this. Okay. Now, so why did I bring up that funny relocation example? So remember unit programming, which was basically no translation or protection. The application runs in the same place in physical memory since there's only one application, and therefore we can link it exactly once and just load it, and we don't have to relocate it on the fly. And this seems like a very boring scenario. One application only, one thread, one everything. But what's nice is the application can always know that it's going to have the address 0 under its control, and so we can link everything once and load it into that memory, and it'll just work as long as I load it at the place it started or was supposed to be loaded at. Okay, but none of us want this. What we'd like more is multi-programming, and so here we have something like MS-DOS from once upon a time, and what's interesting here was that this literally was the case where to have more than one thing running, you actually had to relocate the program in different ways depending on where you put it. So if application 1 and 2 are the same application, they look different in memory because one's linked for a different spot in memory. Okay? And Of course, in this solution, there's no memory protection, and so bugs crash everything. Okay, but the way to look at the problem, there's many problems with MS-DOS and this whole scenario here, and that's, by the way, see, starting MS-DOS over on the right. Basically, one of the biggest issues here is the applications don't have the same address space every time they're running. Because application 1 has an address space that includes 0, application 2 has an address space that includes 20,000 hex, but it doesn't have 0. So application 2 doesn't get 0. And so the nice thing about a virtual environment is that we can give 0 to every application, or making them think they've got 0, even though they don't really have 0. That's what the point of virtual memory is. Okay, it's really about making sure everybody has a consistent view, among other things. And so here's a view with protection. So can we protect programs from each other without translation? Sure. So we can get rid of the issue of application 2 trouncing on application 1 by having some extra hardware registers, a base address and a limit address, that basically says that if application 2 ever strays beyond its little jail cell, then we will stop it from doing that. Okay, so we can put protection on here, but that doesn't require translation. But it still requires that we do linking on the fly when we load. Okay, so what can we do that's different? And this is really the topic of the rest of today and next time, is basically address translation. You can think of it this way. The CPU is working on virtual addresses, and memory is working on physical addresses. And so basically the CPU is reading and storing and whatever from memory using addresses that don't really exist, including 0, right? I told you, wouldn't it be nice if every application got 0? And what happens is it typically goes through something called the Memory Management Unit, MMU, and that MMU turns it into the actual physical addresses that are in use. Okay, and those physical addresses say where the memory really is. So even though application A is running in process A, thinks it's using address 0, it gets translated by the MMU into some actual physical address where the particular 0 for that application really lives. Okay? And so this brings us back to the address space we talked about earlier in the term, which is all the addresses and state that a process is allowed to actually touch. And because of this translation mechanism, we can give every process the view as if it's got the same address space as its neighbor. It's just they're different because they're virtual. Okay, and actually I took a slide out, which I realized I want to bring back to you here. Hold on. Let's see, where did I put it here? Hold on. So you remember this from earlier in the term, which is this idea that program 1 has an address space that has code, data, heap, stack, and program 2 has an address space that has code, data, heap, and stack. We go through different translations for program or process 1 and process 2, and as a result, the code for process 1, even though it might start at 0, gets translated to a particular part of physical memory where the code actually resides, and the code for program 2 gets translated to a different part of physical memory. And both of those can be linked as if they were to start at address 0, even though they don't, because the processor, who's the one that's actually going to use that data, is going through a translation process transparently. Okay? Everybody with me? Now we're gonna talk a lot about what kind of translation's good in that scenario. Okay, so let's return. I'm going to put that slide back in, by the way, before I finish this off. So we really have two views of memory. We have the one that the CPU's got, and we've got the one that the memory has, and those two are different. And translation is essential to basically give us protection, because by translating, we can make sure that program 1 and program 2, or process 1 and process 2, even though they're using all of their addresses they possibly could come up with, can't collide in physical space because we don't translate it that way. By translating process A's addresses differently from process B's addresses, we can make sure that they never collide with each other. And therefore we get protection. Yes?
So how come I can say, use BDB to look at the machine instructions of some other process?
Now, this is not to say that we always set up our translations so that process A and process B can't overlap. It says that we have the mechanism where we can have A and B have completely separated, using the same addresses and never overlap. But we could selectively break that. So the power of this MMU idea, which I'm going to take you through, the power of translation, is by default, the translation can be set up so there is no overlap. But I can selectively decide which addresses in B and which addresses in A actually map to the same physical address, and suddenly I have communication. So think of this as there's barriers, but I can selectively put holes in them. Okay, and that when you're asked the question about how does GDB attach to another process's memory space, it's because there's communication that I've set up explicitly there to allow that. I'm allowing communication, not, they just sort of were searching around and they happen to overlap each other by accident. So it's giving me controlled overlap, and that was one of my 3 things from a slide earlier. Okay? And basically, the other, as I've said this several times, with translation, every program can be linked and loaded exactly the same way. And so now we're back to what everybody that raised their hand, the 3 of you, expected, which is I link the program the same way no matter where it ends up in memory, because I link the program the same way it always ends up in the virtual address space exactly the same way, even though it might be who knows where in the physical memory. Okay, good. And so here was a very simple change on what I showed you earlier with base and bound. This showed up in the original Cray 1, which was this idea, and we already talked about this earlier in the term, of the virtual addresses come out of the CPU, we add a base to them to get our physical address, and we have a limit to check, and if the CPU's virtual address is bigger than some number, we have an error. Otherwise, we add to it, and now we get these protected regions of memory where everybody kind of gets their 0. Everybody has their own 0, even though they're not overlapping in physical memory space. Okay? And this gives the program the illusion that it's running in its own dedicated machine. And, just, are there questions on that? Because I want to show you one quick consequence of this, and then we're going to finish up. So if you look, here is kind of what we end up with if we do this very simple base and bound. Notice that every process in this model has to have a contiguous chunk of physical memory starting at a base and no bigger than the bound. And while process 2 is running, its base and bound, its base is set to this address in physical memory, its bound is set to however many bytes this is, and as long as it uses addresses starting at 0 and going no larger than the bound, process 2 is happy. But at the moment it tries to go negative, which negative addresses are typically bad, or positive above its bound, it fails. And now we have protection. Everybody with this very simple idea of translation? And every version of process 2 can be linked in exactly the same way, no matter whether process 2 is in this part of physical memory or higher or lower or whatever, because the processor is always executing the same addresses that are added, the base is added to them. Now the issue here, of course, is when process 2 finishes, we got a big hole, and then we might put process 9 in there, and we end up with fragmentation. Okay, that's going to be our next major topic. And you can kind of imagine, here we are in a scenario, several process lifetimes later when we can't put process 11 in because it's too big for either of those 2 holes. What do we do? How can we fix that? That's right. So we'll have to swap out, we'll have to copy 10 up somewhere else so that we have space for 11. Yep. Okay, good. So, in conclusion, we talked about starvation versus deadlock. Starvation is a thread waits indefinitely. Deadlock is a circular waiting for resources in the type of starvation. We talked about these crucial 4 conditions for deadlock: mutual exclusion, hold and wait, no preemption, circular wait. And everything we said that says detect deadlock had all of these guys. Any way of avoiding deadlock removed one of them. Okay? And we talked about techniques for addressing deadlock. including allowing the system to enter deadlock and recover, ensuring the system will never enter deadlock, and ignoring the problem and pretending that deadlock never exists. This is unfortunately the solution taken by most operating systems. The second thing we talked about is that memory is a resource that must be multiplexed, and we talked about the advantages of controlled overlap translation protection. We talked about very simple protection through what we're going to come to call segmentation, which is a base plus limit registers, and that's going to be our next topic. And we're going to show that segmentation by itself is not so great, so we're going to get to page tables next time very rapidly. So I hope you guys have a great Monday, have a great Tuesday, and have a great part of your Wednesday, because boy, Wednesday's lecture is going to be totally fabulous. Or not. See you guys.